Hello. Sir, am I audible?
Yes,
Okay. On the behalf of Electrical Engineering Department of Tulsiramji Gaikwad Patil College of Engineering and Technology, I, Radharaman Shaha, Head of Electrical Engineering Department, welcome you all for the AICT sponsored Prerna scheme. And today's expert lecture is delivered by Dr. Bhooshan Rajpathak sir from VNIT Nagpur. Sir has done BE in Instrumentation Engineering in 2002 from Mumbai University, MTech and PhD from IIT Bombay in 2006 and 2016 respectively, and in power system engineering and one in control system engineering. Sir has many publications to his credit in journals of repute and also in national and international conference. So, sir, I welcome you for this session, and from the department, I welcome you for the today's session. Now I will transfer you the session, sir.
thank you, sir, and thank you for inviting me here. Uh, I'm very much pleased to present in front of you some of the points related to control system for electrical engineering in GATE. I hope I am audible.
Yes, sir.
Okay, so if you go through the GATE syllabus, if we start presenting, is it visible, the screen?
Yes, sir.
Okay, so this is the updated GATE syllabus, which will come into effect from 2021. Uh, so there are quite a few changes as far as electrical engineering concerned, in especially in machines and electronics and power systems. But as far as control system is concerned, the syllabus is more or less same. So we have a mathematical modeling, representation of systems, and then block diagram, signal flow graph, transient steady state analysis of ATI systems, stability analysis using Routh-Hurwitz, Nyquist, Bode, root locus, and then compensator, lag lead, and PID controllers, tuning, and then state space model, solution of state equations, RMS and average value calculations for general periodic waveform. So this is typically the syllabus for the university undergraduate course, the control system course. So almost all the topics are covered in our undergraduate course here. The more important point to note is in GATE only numerical questions are asked. So we have to develop this habit of solving these questions very fast if you want to attempt the full paper or the maximum portion of the paper. In control system, there are some problems which takes large amount of time due to computations. So in this exam, this particular session, we will explain some of the tricks by which you can solve the questions easily and save the time. Okay, so some shortcut methods I will explain in this lecture. Okay, so we will start with the topic called state space. Am I uh, visible here? I am writing on the open board. So I hope whatever I am writing, you are able to read it. Okay.
Yes.
Okay. So state space is typically a topic which is, I would say, neglected in our university syllabus because we start with time domain analysis and then frequency domain, and then in the end, mostly the state space is covered. So these concepts, they are not that much developed because the time is very less to complete this topic. That is the typical case in most of the colleges. But in control system, if you ask me, this is the easiest topic to study and understand. And all the modern day control system is based on this state space. That is why understanding this state space is very important. Okay. So in brief, I will explain why the state space is necessary and why the state space has gained so much of popularity. So we start with a very simple circuit. So this is series LCR circuit, a very well-known circuit. Now, if you are asked to write down the circuit equations, so what will be circuit equations? V in of t will be equal to L di by dt plus R into I of t plus 1 by C integral of yes I dt, and VO of t will be equal to 1 by C integral of I dt. These are the circuit equations. Now transfer function, what it does is we get this VO by V in of S, which is our transfer function. So for transfer function, what we do for to obtain this TF, the first step is convert circuit equations by taking Laplace. Okay, so we take Laplace transform of these equations and we get V in of S and VO of S, and then the ratio is transfer function. Now the advantage of transfer function is as you change the input. Okay, so from this transfer function, VO of S will be equal to, let's say transfer function is denoted by H of S into V in of S. So as we change this input, what will be the effect on output? That can be mathematically calculated or guessed by this transfer function. Okay, so as input changes, how output will behave. That is what you get from transfer function. So this is the advantage. Now what is the disadvantage or drawback of transfer function method? If at any time I want what is the voltage across this, what is the current in this, what is the voltage across inductor, okay, or what is the voltage across capacitor. Now since VO is voltage across capacitor, okay, we can obtain it. But what is the voltage across this inductor or this resistor? So all these things are not obtained directly by this method. VO of S is HS into Vn of S. Okay, because transfer function will only give you change in output when there is a change in input, because we are having a ratio here. So all these internal components and internal variables, these changes or these quantities cannot be directly measured or obtained by transfer function. Now, if you increase the complexity further, so let's for discussion consider this circuit. So I have this and I have another loop here. So let's say this is L, R, this is C1, C2, and this is R2. So now output is taken across R2. I want to know what is the value of voltage across this capacitor C1 at any given time t or C2. Then these kind of quantities are not obtained by transfer function. So this is the requirement typically in a very complex plant. You require voltages across, if it is electrical circuit, nodes or loop currents or components. In any chemical plant, you might be interested in at particular location what is the temperature, what is the pressure. So these kind of things are required in practice, but in our transfer function approach, we get just output by input. So that is one drawback of this method, transfer function method. The second drawback of transfer function method is, if let's say I have a system which has three inputs. So let's say my input is U1, U2, U3, and this is my system. And I have two outputs, Y1 and Y2. And if I ask you, find out whether the system is stable. With transfer function, we know how to obtain the stability. You have transfer function, so you find out the roots of the characteristic equation, and then using Routh-Harry method, you can get the stability, or root locus method. But now when you have three inputs, that means multiple inputs and multiple output. Now how you will check the stability? Obviously, for this case, what we will have to do is, we will have to consider all these combinations. That means y1 by u1, y1 by u2, y1 by u3, the transfer function. Similarly, y2 by u1, y2 by u2, y2 by u3, these transfer functions. So how many transfer functions we need to consider? All of them. 1, 2, 3, 4, 5, 6. So if you have typically n inputs and m outputs, okay, if this is n and this is m, then you require n into m transfer functions. And for all transfer functions, you will have to find out the characteristic equation. You will have to find out the roots. You will check whether these roots lie in LHS by either root locus method or Routh-Harry method, and then you can comment on stability. So how difficult it is when number of inputs and outputs are increased. You can understand it is n into n. So if you have 10 inputs and 10 outputs, it will be 10 into 10, that is 100. 100 transfer functions we need to check. Now you can understand that if practically we want to use this transfer function approach, then in any complex or large plant, there will be hundreds of inputs and hundreds of outputs. Typically, you can consider a plant like a refinery, okay, where there is a petroleum refinery where you are obtaining several outputs there. You obtain petrol, you obtain diesel, you obtain the hard oil. So many outputs, paraffin, and you have multiple inputs. Now in this kind of systems, the transfer function approach is not suitable. It is time consuming and very tedious. And this is the motivation for state space. In state space, this problem is solved very easily because we have matrix representation. So the system which has multiple inputs and multiple outputs, which are typically called MIMO systems, in that state space is the best method. And modern control system is based on state space because almost everywhere now we have multiple inputs and multiple outputs. So state space is used everywhere. And the second advantage is what we discussed earlier, internal states, internal states like voltages across these components or current in the particular loop. So internal states can be obtained at any given time by the state space representation, which is not obtained in the transfer function. You just know what is output and what will happen to this output if the input is varied. Okay. So these are the two important advantages of state space. That is why state space is used. Okay. Now, the typical problem which we face in state space is this, and what is important with respect to gates, the typical problems. The state transition matrix, solution to state equation, controllability, and observability. So these are the three important points on which the questions are based in GATE. We will see this first, controllability, the concept, okay, and the observability concept. For single input, single output system, we already know the notion called stability. Okay, so stability, what we mean by stability, it is denoted by this term BIBO, that is bounded input, bounded output. If the input is bounded, the output need to be bounded. Okay, that means your output cannot go to infinity. It should remain in some constant value or steady state value. Then the system is called stable. So that is the notion of stability, which is true in state space also. But apart from this notion of stability, we have another notion called controllability. So this needs to be understood because problems on controllability and observability will require this notion. Finding controllability is easy, but very few times they will directly ask you to check controllability. How to check controllability, that almost everybody I think knows. You just need to form this matrix called controllability matrix B, AB, A square B, and so on. Okay. If A is n cross n, then it will be last entry will be A raised to n minus 1b. And this matrix, if it has full rank, the system is controllable. That is the mathematical check for finding out controllability. But the questions will be asked on the concept of controllability. Okay. So what is controllability? So that will be clear once we have the state equation. So let me write down this. The state equation is for x dot t is equal to a x of t plus b u of t. So this is called state matrix. This is called input matrix. Okay. And this is our state vector. Okay. And the output equation is y of t is equal to cx of t. Okay. Now, if we convert these state equations by Laplace transform, then we get x of s minus x0, assuming some initial conditions, into s, because this is a derivative, ax of s plus b u of s. I am using capital letter once we convert into Laplace. That is the standard form. And now we can have si minus a x of s. Since these are vectors and matrices, so where we are multiplying, that also matters. Okay. We cannot write this xs into si minus a. Si minus a will come in this side only because a is multiplied by this vector x of s will be equal to b u of s plus x0. And now we are saying if Si minus A is invertible, if the inverse exists, then we can say x of s is Si minus A inverse b u of s plus Si minus A inverse x0. Okay. Now here one more point to understand uh, that I will explain here. This Si minus A, where S is our symbol, I is identity matrix, and A is our state matrix. So we are taking inverse of that matrix, and then we are multiplying B into U of S. Now, if you want the solution of state space, then we should take the Laplace inverse here. So x of t is equal to Laplace inverse of Si minus A inverse B U of S plus Laplace inverse of Si minus A inverse x naught. I am taking this x naught outside this Laplace inverse because x naught is a constant. So you can take the constant outside Laplace inverse. Here we cannot take anything outside. Now we have this Si minus A inverse B U of S, the Laplace inverse of this, and Laplace inverse of Si minus A inverse. So Laplace inverse of Si minus A inverse is called phi of t. Okay, this is called state transition matrix. Laplace inverse of Si minus A inverse is phi of t, state transition matrix. This is extremely important. Typically for LTI system, this will be represented by e raised to at. This is called state transition matrix. Okay, this is phi of t is equal to e raised to at only for LTI systems, linear time invariant systems. Okay, now if we have this Laplace inverse of Si minus A inverse is phi of t, so obviously I can write phi of s is equal to Si minus A. So xt, which we are interested in, is essentially phi of s b u of s plus phi of t x naught. Okay, so this u of s is one function of s, phi of s is another function of s. So if you have this u of s and phi of s, and if you are taking Laplace inverse, that means multiplication in s domain. Multiplication in s domain will result in convolution in time domain. That is the property of Laplace. So this will be equal to 0 to t phi of t minus tau b u tau d tau plus phi of t x0. And since we will deal with LTI systems, even in GATE, we are dealing with LTI systems only. So you can write this as 0 to t e raised to a t minus tau b u tau d tau plus e raised to at x0. This is x of t. This is called solution for state space. Okay, and xt is our state vector. See the advantage of state space which we discussed, two advantages. In that, one advantage is any state you can obtain, okay, for any time t. So that is given here. So you can decide what time t you want. At that time t, you just solve this and you will get the value of state. So your states can be for electrical system, as we have seen earlier. It can be voltages across the components or the loop currents or the nodal voltages, whatever are your states as you defined it. You can obtain at any time t, you can obtain those values. You just need to solve this state equation. And that is why solving this state equation is extremely important if you require values. Okay. Now, okay, so the trick part which I explained, so that we will see. I hope up to this point there is no doubt. Is there any doubt? The solution of state space. So what we did, let's recollect. So we have this state equation. We converted that state equation using Laplace transform. Then we rearranged the term and we got x of s in terms of u of s and x0. Then we just took inverse Laplace x of t. When we take inverse Laplace, Laplace inverse of Si minus A inverse is C of t. That is state transition matrix. And here we have multiplication in Laplace domain. One function and another function. So if you have multiplication in Laplace domain, if you take Laplace inverse, it will be convolution in time domain. That is why we have e raised to a t minus tau b u tau d tau plus e raised to a t x naught. Solution for state space. Okay. Any doubt now?
So, if students have any doubts, you can add in the comment chat box. Okay.
Okay. So I will continue this. Now, see the concept of controllability, how it is developed. If I want to change my state from any time t1, x of t1 to some another value, first question is, can I change this arbitrarily? For example, let's say I have one 3 by 3 system and my state is at one time, let's say 1, 1 and 0. And I want to change from 1, 1, 0 to, let's say, value minus 1, 2 and 3. I want to change my x of t from this to this value. At some time t1 I have this, and at some time t2 I want this. This can be anything, t2 value. Is it possible to change from this to this? If it is possible, then what will be the input? That is another question. But let's say if input exists, is it possible to change from this to this? Second question, let's say if this is possible, is it possible in finite time? Okay, so it should not take infinitely many time. That means time t tending to infinity, if I can change this, that is not allowed. In finite time, I should go from this value to this value. Is it possible? And now we go one step further. If this is possible, then I am saying from any A, B, C, some initial value to some X, Y, Z final value. Arbitrary. Okay, this is called. So arbitrary changes from any given to any final in finite time. Is it possible? If it is possible, then the system is called controllable. Okay, so I will write this in the next page. For a system AB, okay, system AB means system defined by the state equation x dot equal to ax plus bu. For a system AB, if transferred from any given initial state to any final state in finite time, then system is called controllable. If it is not possible, then the system is called uncontrollable. So please understand this difference between stability and controllability. Here we are not checking the stability, bounded input, bounded output. No, there is no concept of output here. We are just interested in state equation. That is why we are saying system AB. That means x dot equal to ax plus bu. Only that state equation is sufficient. That state equation will give you this solution of state space. X of t is e raised to at x naught and this integral. Now we are saying instead of x naught, I can have any state here, initial state that need not be starting from zero because this is time invariant system. So if you change the time, it will not affect this. So I am saying any given initial time, I can have any arbitrary value and I want to change to any different value, arbitrary value again. I should be able to do it. If I can do it, then the system is called controllable. Okay, so you can guess, understand this or imagine this how uh, strict this definition is of controllability. We are seeing any final value from any given initial value in finite time. Obviously, for all these changes, input will not be changed. You are allowed to have different input. You can use different input. How to find that input, that is another problem. Okay, and then that goes into another domain. How to find that input. So that also is one part in control theory, though it is not part of gate. So we will not discuss that. But different inputs are allowed. You can use any input. But I want to change from this to this. And not only one specific. Any given I can give you and any final I can give you. The time taken can also be different, but I should be able to do it. If that is possible, then the system is called controllable. So controllability is completely different from stability. So for understanding, I will draw these two circles, Venn diagram. Okay, this is set A, this is set B. Let's say set E is stable systems, set B is controllable systems. So these two sets, they are not subsets. They can have a finite intersection. So all the systems in this will be stable and controllable. Systems here will be only controllable but might not be stable. Systems here are stable but might not be controllable. So controllable and stable, they are not subsets. So it doesn't mean that system is stable means it has to be controllable. No. Similarly, if system is controllable, then it has to be stable. No. Okay. These are two different notions. Okay. And this is asked in the gate. A system is stable, so it implies it is controllable. Okay. These kind of questions with uh, twisting the languages, they are asked in the gate. And many times students commit mistake here. So you have to understand that controllable doesn't imply stable. Similarly, stable doesn't imply controllable. These are different notions. Okay. Now, one more point is observable. So that controllable we have seen. So when we have these two equations, y equal to cx and x dot equal to ax plus bu, then another question which can be posed here is, let's say we have some knowledge of output over some period of time from some 0 to t. Output is available to us. The input is also available to us over that period 0 to t. So u is available, b and y is available. Now the question is, can you predict what are the states at time t? Okay. So can you observe the states at time t when the input u is available from 0 to t and output y is also available over 0 to t? So can you predict or calculate the value of x states at time t? If you can, over all such t's, provided u and y are available, then the system is called observable. That means you can observe the states. You don't need to calculate every time. By just getting this input and output, you can observe what are the states. Okay, the system is called observable. Similar definition is there for a system AC. Instead of AB, now AC is observable if for u and y from 0 to t, the state x of t can be calculated or measured. Okay, so that system is observable. So system can be controllable and observable, but might not be stable. Similarly, a system can be controllable, but may not be observable. System can be observable, but may not be controllable. Okay, so all these things are different. One doesn't imply second, second doesn't imply third. Okay, so one best example, and this also once or twice asked in the gate. Okay, long back I think, and this is very simple but intuitive example, and many students, if they are not aware, they commit mistake here. All of you know this. This is bridge, a Whiston's bridge, where you have four impedances. Okay, in Whiston's bridge you have resistances, and one of them is unknown. And how you find it? When the bridge is balanced, then you have Z1 by Z2 equal to Z3 by Z4. That is how you get the balance with Whiston's bridge. Okay, or for any bridge. Okay. Now, assuming that bridge is balanced, that means galvanometer shows no deflection. That means no current flows through this. That means these two are equipotential points. This point and this point are equipotential points. That is when the bridge is balanced. I am saying, let's say, instead of this G, I am saying here I will denote this as my VO and this as my V in. So I am measuring output across these 2 points and input is given across these 2 points. Okay, and at the instant of balance, okay, at balance, my VO will be 0 at balance. Now I am asking you the question, at this balance when VO is 0, is the system stable? Is system stable? Okay, the answer is obviously yes, system is stable because as you change the input, your output is 0, so it is bounded. Output remains bounded. It is 0. So system is stable. So system is perfectly stable. It is not unstable. Your output is not going to infinity, even if you change the input. Okay. Once your bridge is balanced, is system controllable? So any student who want to attempt this, is the system controllable from our this definition of controllability? We have seen this definition. So is this system controllable at balance? The answer is no. Okay, this looks strange. The answer is no. The system is not controllable. Why system is not controllable? Because see the definition, from any given initial state to any final state. Okay, by applying some input in finite time, we should be able to vary the system. Now, if my state is this particular, then whatever I change the input, this voltage will be always zero. It will not change. So whatever input you apply at balance, nothing is going to change in this point. It will be always zero. Okay. So no matter what input you apply, this will be always zero. So you don't have any control over this at balance. For to change the balance, you need to change some of the components. Only thing that will change the balance is changing the value of component. Okay. Otherwise, if the components values are fixed and if you have obtained the balance, then the balance will not change by changing the input. So that is why system is not controllable. You cannot change the states once the balance is obtained. So this is one best example to understand the concept. This system is perfectly stable, but it is not controllable. Okay. Now SS to TF changing. This is typically required in gate transfer function you need to calculate from state space. So SS to TF, when you have to convert, what is the formula? TF is equal to C into SI minus A inverse into B. Okay. So you can check this from our previous discussion also. So X of S we had obtained as SI minus A inverse B US plus SI minus A inverse X0. And the second equation is Y of T is equal to C X of T. So if you convert this also in Laplace, it will be Y of S is equal to C X of S. Now if you plug this value of X of S here, then it will be C into SI minus A inverse B U of S and plus this initial condition. For transfer function, initial conditions are always 0. Okay, and that is why you get this. And this is important point, by the way, to remember. Okay, so I will emphasize this thing that time. This I will again revisit to emphasize the point. This is called complete solution of state space, solution for state space. it has two parts. This is one part and this is another part. Okay. This is called zero input response, and this is called zero state response. So the x of t is comprised of two parts, zero state response and zero input response. If you are interested in transfer function, then we assume all the initial conditions zero. Okay. So this part is neglected in the transfer function. Only this part is considered. Okay. So in transfer function, you require this. Now Si minus A inverse B and C, if these are there and you want to compute it, let's say you are talking about A, which is 3 cross 3. Okay. So there are several elements here, total 9. First, you will have to find Si minus A. Okay. Which will be S0 0 0 S0 0 0 S minus your A matrix. That will be Si minus A. Then you are going to find out the inverse. So let's say Si minus A we denote by phi of S. So we are finding the inverse of phi of S. So how to find inverse? Adjoint of Si minus A divided by determinant of Si minus A. That is inverse. Okay. Typically, the determinant is denoted by this Si minus A, and adjoint of Si minus A is nothing but cofactor of Si minus A and the transpose. Okay. So for 2 by 2 it's okay, but when you have 3 by 3 system and when you calculate the inverse, what you actually do, this Si minus A, every element's cofactor you find. Okay. So how you find cofactor? If you want to find the cofactor of this element, then this particular column, this row you will delete, and this small matrix, its determinant you will find. That will be the cofactor. Similarly, if you are finding cofactor of S, then this particular row and this column you will delete, and then remaining elements determinant you will find. And not only that, you will multiply by either plus 1 or minus 1. So first element is plus 1, then minus 1, then plus. Similarly, then minus, plus, minus, and then again plus, minus, plus. So this way you will multiply that determinant. That way you will get the cofactor matrix. So for every element you will get the cofactor. So 9 elements for 3 by 3 means 9 cofactors. Then you will take the transpose of it. That will be adjoint. And then you will divide the determinant. Okay. So the trick is typically the C matrix will have this kind of entries. Some non-zero entry here. Let's denote this by alpha 0 0. Then this is our Si minus A inverse, and B matrix will have entries from 0 0 and beta. Okay. So if these are our entries, alpha 0 0 0 0 beta, this beta can be here also 0 beta 0 depending upon, but one entry will be non-zero typically, remaining entry is 0. Similarly in C, one entry will be non-zero, remaining entry is 0. Then the trick to save the time to get this C Si minus A inverse B very fast is this. Okay. Please understand this carefully. The trick is you first multiply let's say by alpha to this matrix, what will happen if this matrix has entries here, here, and here? If you multiply by this, then alpha into 0, 0, alpha into 0, 0, alpha into 0, 0. That means you are just taking this row. These rows are multiplied by zeros. Okay. So essentially only this row is selected and this row is getting multiplied by alpha. So you will have basically this row of this matrix multiplied by scalar alpha. Now you are multiplying by 0, 0, and beta. This row has three entries. So if you multiply by beta and remaining zeros, that means you are removing these entries. Only the last entry is getting multiplied by beta. That means only this last entry is required. To this last entry, you are multiplying by alpha and beta. Are you getting it? To this matrix, if you are multiplying by alpha 0, 0 and 0, 0 beta, let's take one example if you are not sure. So a very quick example. So let's say my one matrix is 1, minus 1, 2, 3, 4, 5, minus 7, 11, minus 9, and I am multiplying by 3, 0, 0 and 0, 0, 5, let's say. So you can check first row, first column. So this will be just 3, then first row, second column, minus 3, first row, third column, 6, and then I am multiplying by 0, 0, 5. So 0 into 3, 0 into minus 3, 0, and 6 into 5. So 30. So the final answer for this will be 30. Okay. How 30 comes? 2, 3, and 5. So this is 3 into 5 into 2. That is 30. So we are saying 3 into 5. This is our alpha entry. This is our beta entry. 3 into 5 into 2. This entry. So if you are multiplying, pre-multiplying by C and post-multiplying by B, and if B has all entries 0 except one non-zero, similarly C has all entries 0 except one non-zero. Typically these are the C and B you will face in the exam. Then this multiplication is essentially this entry multiplying by this and this. So no need to do all the multiplication. Now if this is the multiplication here and this matrix we are saying is our Si minus A inverse matrix, which is nothing but cofactor of Si minus A transpose divided by determinant of Si minus A. Determinant of Si minus A is a scalar quantity, so that you can take. You are basically multiplying cofactor of Si minus A transpose by the C matrix here and B matrix here, where this is non-zero and this is non-zero, or some entry non-zero. Okay, so only that element cofactor you want. No need to calculate all the cofactors. Okay, so if you want to calculate the cofactor and if you are taking transpose, that means with original Si minus A, you are taking cofactor of this. Okay, or here, because after transpose this entry will go here. So just take cofactor of one element, multiply by C and D. That's all. That is how you can directly get the answer here. Okay. So this trick is very useful if you are solving the questions where you are calculating 3 by 3 entries. Okay, or 3 by 3 matrix. So I will give you one example to test this. You can try at your end. So let's say 1, 0, 0. I want to find out transfer function, and my Si minus A matrix I will write here. So it is S 0, 1, 0, S plus 1, 0, and minus 1, 2, S plus 3, and I want inverse of this, and here my entry is 0, 0 and 2. So by this trick you check and calculate this. What is the trick? This is my Si minus A. So I will get the cofactor of Si minus A, and then I will take the transpose. Cofactor of Si minus A means every element's cofactor, but no need to calculate. Now we know, since this is first entry and this is last entry, that means only cofactor of this thing is needed. So you just take cofactor of this thing, which is 0 minus S plus 1. Okay, minus of S plus 1. That is the cofactor, because after transfer this entry will come here. So just S plus 1 into minus 1, and the cofactors, how you multiply? This will be plus, cofactor will be multiplied by plus, minus, plus, minus, plus, minus, and plus, minus, plus. So whatever cofactor we get, that will be multiplied by plus 1. Okay, so the same thing, minus of h plus 1 divided by the determinant. So you get the determinant of this. That will be the transfer function. You can check it. Okay, so this is about the state space. In the state space, again I will revise and then we'll go to the next point. These three are important: solution to state equation, controllability, observability, questions on this, and state transition matrix. State transition matrix is phi of t, Laplace inverse of Si minus A inverse. Okay, so these things you can calculate. Okay, now let's go to the second point. Bode plot. Okay, in Bode plot, I will not explain the method because I will assume that you are already familiar with the method how to calculate Bode plot. So I will not go into this. The questions which are asked are on the very tricky part. So I will give this example here. The gain when it crosses 0 dB line, okay, it is called gain crossover frequency. So this frequency is omega GC, and phase when it crosses minus 180 degree line, it is omega PC. Now in this graph both are same, omega GC and omega PC. So when omega GC is equal to omega PC, is system stable? This is a special case when omega GC is equal to omega PC. Is system stable? The answer to this is system is marginally stable. In our time response, you must have observed that when the roots lie on j omega axis, then we say system is marginally stable. If roots lie in LHS, system is completely stable. If roots lie in RHS, system is unstable. and when they are on j omega axis, system is marginally stable. Similarly, this is the case when omega gc is equal to omega pc, system is marginally stable. Okay, so this is the special case. Okay, now the question is, if TF has zeros in RHS, is system stable using Bode plot? So for a system which has zeros in RHS, for example, s minus 1 divided by s into s square plus 3s plus 5. So here the 0 is in RHS. Okay, 0 at s equal to 1. So is this system stable using Bode plot? Anybody here who knows this? The zeros when they are in RHS. For normal systems, Bode plot you already know. So how to draw it, how to check the stability. But these are some special examples. When zeros are in RHS, these systems are called non-minimum phase systems. Okay, these are special systems which are called non-minimum phase systems. And typically the problems will be asked, if they are tricky problems, they will ask this kind of problems. Okay, so when zeros are in RHS, these systems are called non-minimum phase systems. The properties of non-minimum phase systems are different from our normal systems. One of the properties I'll explain later. For this system, the Bode plot method fails. Okay, whenever your poles and zeros are in RHS, the Bode plot will not give accurate results. So you have to understand this, and that is why the Nyquist plot is necessary. Okay, sometimes we get this, we wonder why, if we study Bode plot, why to study this very complex concept of Nyquist plot. The reason is, when the system's pole and zeros are in RHS, then the Bode plot method will not give you accurate results. Okay, the phase plot, when your go zero is in RHS or pole is in RHS, will be different, but the gain plot will be same. So for this system and the system with s plus 1 and the same denominator, s upon s square plus 3s plus 5, and I will encourage all of you to try these two examples in MATLAB or manually also, and convince yourself that for these two systems the denominator is exactly same, no change in the denominator here and here, but here the 0 is in RHS, here the 0 is in LHS. Both the systems are actually stable systems, but Bode plot will give same magnitude plot for both the systems. Okay, so I will write here, you can check it. Same magnitude plot and different phase plot. Phase plots are different because here there is a 0 in RHS, so there will be uh, different angle contribution by this 0. Okay, in tan inverse, your imaginary and real, if both are not positive, I will give small reason to understand. This is how you measure the angle. in this direction, if angle is measured, this angle is called positive, and if we measure the angle in this direction, this angle is called negative. So if theta is the angle, then y by x, tan inverse of y by x, okay, both are positive. That will give us positive angle. But let's say if I am asking you to measure this angle, this is my theta. Now here x is negative, this is minus x, and y is positive. Okay, so you need to measure angle in this case like this. You cannot measure this negative angle. You have to measure this angle. This angle will be called 180 minus theta, and then you have to take tan inverse of that. So this 180 minus theta thing will change the angle contribution when our zeros and poles are in RHS, and that is why you should remember this thing. If you have same denominator but 0 1 in LHS, 1 in RHS, then the magnitude plot will be same, phase plot will be different. Okay, and that is why Bode plot method fails. It will not give you accurate results, and here you require Nyquist plot. So you can check this by drawing the Bode plot for the both of these examples. Okay, and there is one more peculiar example. So in this lecture, I am taking only these kind of special examples which we generally do not encounter, because these are the questions which are asked. And then I will keep 10 minutes. If you have any doubts regarding any concept, you can ask me. Yes. So this is again very special example, and many times student commit mistake here. Let's say my GS is equal to 1 by S. So my transfer function is just one pole at origin. Okay, if you draw the pole zero graph, it is one pole at origin. My question is, if I have one pole at origin, our normal understanding says if your poles are not in RHS, your system is stable. In that, if you have one or a pair of pole on j omega axis, your system is marginally stable. If you have repeated poles on j omega axis, your system is unstable. So this is not a repeated pole. This is single pole on j omega axis. So is this system stable? From that definition, we can say that system is stable. What is our definition, or what is our notion basically? Our notion is if our roots are not in RHS, then the system is stable. So root is not in RHS, so system has to be stable. Also, there are no repeated roots on j omega axis. So we will call this system stable. But now you see, for a stable system, if you apply a bounded input, you should get bounded output. Okay. So if this is your transfer function, then if my input u of t, I apply step input. Okay. My input is this step input u of t. So in the Laplace of this input will be u of s. What will be this? 1 by s. Okay. This is my step input 1 and 0 for t greater than equal to 0, for t less than 0. So 1 by s. Now what will be the output here? Cs will be equal to 1 by s into r of s, which is again 1 by s. So 1 by s square. So what will be c of t? Laplace inverse of 1 by s square. is T. So my output will be like this. This is my output, C of T. And my input was bounded, but output is increasing. It is not bounded. Clearly T, if it is my output, it is not bounded. So with bounded input, I am not getting bounded output. Then according to my Bibo stability criteria, this system is not stable. Okay. So this is again a peculiar case where even though your root is not in RHS, there are no repeated roots on j omega axis, still your system is unstable. Okay. So questions are asked by twisting the language in different terms, but essentially the question means if you are uh, you are having single root at origin, is system stable? So the answer should be no, system is not stable. Okay, this is the reason. Your output will increase and it will go to infinity. Okay, is it understood? Okay, then one more peculiar example. Uh, okay, so here is one case. Okay, so the question is a system, one system has response to a step input. That means its step response is like this, indicated by this colored graph. So it will start from zero, it will oscillate, and then it is stabilizing. Okay, so steady state is reached. Another system has step response like this. It goes into negative direction first, and then it stabilizes. So will we call this system stable? This will be called stable, that we already know. This is a stable system that we have, you must have already studied in your course. Response going from zero to some value. So you achieve one peak. This is the highest peak achieved, peak overshoot, and then you basically achieve stability, a steady state. Okay. So this is your peak time, TP. and then you this is your PS settling time. But in this system also we are achieving peak. Ultimately we are settling down, but we start from this negative direction first. Will this system be called stable? So the answer is yes. These systems are also stable. This is called inverse response. Okay, inverse response means you start response from negative direction and then you settle. So I have told you that about non-minimum phase system, right? One peculiarity or special point. So this is one speciality of non-minimum phase systems. Okay, or systems with zero in RHS. So systems with zero are in right hand side. They will have step response or impulse response starting from negative direction, opposite direction, and then they will settle. Okay, this stability is achieved only because of poles in LHS. So system can have zero in RHS, but if its pole are in LHS, then ultimately it will settle because this settling is the property of poles, not zeros. But from where the initial response will start, that will be determined by zeros. If zeros are also in left hand side, then the response will be from 0 to positive. But if zeros are in RHS, response will be from 0 to first negative, opposite direction, and then because since poles are in left hand, so it will stable. It will be stabilized. Okay, so that is the peculiarity of non-minimum phase systems. This response is called inverse response. Okay, for body plot we have seen the systems non-minimum phase systems or zero in RHS, the body plot method fails. It cannot give you the accurate stability because the magnitude plot will be same, but the gain phase plot will be different. Okay, and that is why same magnitude plot but different phase plot for two systems. That means body plot method fails. And that is why you need to go to Nyquist. Okay, so now do you have any points or questions? So that I think I should take now. Yes. Any questions from students? Yes. Any doubt? Any question? Not related to this, but any other doubt related to any concept which is not clear about any topic in control?
Hello.
Yes.
Uh, so students, is there any doubt related to the session or anything related to control system? Or I think students are not having any questions, sir. Single flow graph, can you explain, sir? Uh,
Signal flow graph.
Tejaswini, Yes, Tejaswini Alam has posted.
Okay, signal flow graph. Okay, so yes, there are also some peculiar points. So I'll present first basic concept of signal flow graph. So let's draw one graph. Okay, and let's denote this by okay. So in a signal flow graph, there are different points, uh, different components, I should say. One is called input node, one is called output node. Okay, then we have loops, forward path. So what is input node? Input node is the node where there are all the points or all the paths are going out. Only one path is coming in. Okay, so I will write here. And exactly opposite to this is output node. Okay, so in this example, you can see this is our input node. So there is only one input path and the remaining paths will be output. Now here there is just one. Typically you can have this. So multiple outputs add a single input. Okay, from where your input node starts. So this will be your input node. Similarly, an output node is the node where all your paths are output paths and only one input. This is output node. So this is what we define. We will define what is our input node and output node. Loop is if you start from a node and you traverse through multiple nodes and come back to the same node again without repeating other nodes twice. Okay, so I will write it here. Node and travel through then it is called loop. So if you start from a particular node and travel through multiple nodes without repeating them twice and come back to the starting node again, then it is called a loop. So in a loop, only one node will be repeated and that will be the starting node. So if you, let's say, start from this, you start from this, you travel like this, you come back and you come to the same node again. So all other nodes are not repeated twice, only the starting node you are coming back again. This is a loop. What is a forward path? Forward path is a path which connects input node to output node. Okay, path which connects input node to output node. So in this, there are two forward paths. One forward path is like this, you are connecting. Second forward path is you can travel through this route also, and you can come here. So there are two forward paths. Okay. So these are the components of signal flow graph: input node, output node, loops, forward path, and in between are also nodes. These are just called only nodes. Okay. Out of this, these loops and forward paths, they are extremely important to determine the transfer function. So how to check the transfer function? How to calculate the transfer function? So I will list the steps to find TF. Steps. Okay. First step is identify the forward paths and denote them T1, T2, dot dot dot. So you denote these forward paths. Then identify the loops and denote them L1, L2, dot dot dot. So identify the loops. Then check, are there any loops which are mutually non-touching. Mutually non-touching. So I will explain this in one example. What are mutually non-touching loops? So the third step is always check, are there any loops which are mutually non-touching? Okay. If there are, list them. And the last step is check, are there any loops which are non-touching to forward paths. So these are the four steps. The first step is identify first forward path and denote them by T1, T2. Identify all the loops, denote them L1, L2, L3. Then check whether there are any loops which are mutually non-touching to each other. If there are, then list them. Then check whether there are any loops which are non-touching to any forward path. If there are, then list them. Once you have all these data, then there is a Mason's gain formula. You can use Mason's gain formula to get the answer. And what is the Mason's gain formula? Transfer function is nothing but summation Pi delta I divided by delta. This is called Mason's gain formula, where delta is calculated as 1 minus summation of all loops plus summation of all two non-touching loops minus summation of all three non-touching loops, and so on. That means next will be plus summation of all four non-touching loops. But this kind of example we will never encounter, especially in our courses. So typically the difficulty will be limited only up to this 1 minus summation of all loops. At max there will be some loops, two loops which are non-touching to each other. So all these kind of loops you can add together. Okay. And what is delta I? One minus summation of all loops non-touching to forward path Ti plus summation of all two non-touching. Also non-touching to Ti. Okay, and this can again continue minus summation of all three non-touching loops also non-touching to Ti and so on. But typically up to only this level is sufficient. Okay, so you will not get any difficulty which will be more than this. At max it will be this. All loop non-touching to Ti. At max there will be a pair of loops, two loops non-touching to each other as well as non-touching to Ti. That is delta I. And once you have this, then Ti delta I, their summation divided by delta. Okay. So this kind of uh, system will be there. So let's take one example, or I should say two examples. And these two are special examples. Okay. So this is the diagram. The first thing is to find out by our steps which we discussed is identify the forward path, then identify the loops. So let's start with this. First is forward path. Now you can see in this diagram, forward path is what is our definition? From input node, from input node to output node. All those paths which travels from input to output without traversing through any node twice. These are forward paths. So we have this input, we have this as output. So all the paths which traverse from input to output are forward paths. So let's list them down one by one. One is obviously G1, G2, G3. So traveling from input to output. Okay, that is one. So G1, G2, G3, G2. Then let's travel through G1 and we go to this by different route. So what is the different route? G1, G7, G6. Okay, so I will suggest you draw this forward path to understand. Okay, and you write G1, G2, G3. Okay, and then what is our next? G1, G7, G6. This kind of pictorial depiction will be very helpful when you are taking your answers, that all the things you have considered. Okay, just checking this, you will commit mistakes. So if you have pictorial depiction, it will be very easy for checking. So I strongly suggest whenever you are solving this kind of problems, whenever you are writing this forward path or loops, you draw a small diagram of that. G1, G6, G7. And as a matter of practice, you always write this in ascending order. Okay. So rearrange this and write in ascending order. Okay. T2, T3. Now we have exhausted this path. Now we will try this path. So G4, G5, G6. G4, G5, G6. So the path is G4, G5, G6. Okay. And the counterpart of that, T4, will be G4, G6, G8. So G4, G8 and G3, sorry. G4, G8 and G3. So I'll write this G3, G4, G8. Okay. Then T6, T5 and T6. These are not very straightforward, but you will have to pay attention to the graph. There are two more forward paths which are not straightforward. Can you guess that? Yes. If you have guessed that correctly, it will be G1, then G7. Okay, so I will highlight them first. We are saying G1. We are starting with G1, then G7, and then from here we will go to H2, then G8, and then G3. Okay, so G1, G3, G8, H2, and here the sign is negative. So I will write that with different color to highlight. Okay, and the diagram we will draw with this. So G1, G7, H2, G8, G1, G7, minus H2, then G8 and G3. G7 have not written here, right? And the second one is the opposite. So we can start with this G4, G8, H1, G7, G6. So minus G4, G6, G7, G8, and H2. So how we have found this? G4, then G8, G7, G6, G4, this G8, G7, G6, H1. So now we have listed all 1, 2, 3, 4, 5, 6. Okay, that is how we traverse. Out of this, these are okay, very easy to check. But these things where we are traversing, this will be only clear if we draw this diagram. Otherwise, we can commit mistakes. Now, once we have these 6 forward paths, then we calculate the loops. So loops, I will now not show you. I will directly write L1, L2, L3. Okay. So you can check this minus G2 H1 equal to minus G5 H2 and equal to G7 G8 H1 H2. So the I will suggest you draw this kind of diagrams, sketches, though I am not drawing here. But one loop is G7 H2 G8 H1. So G7 G8 H1 H2. And then the small loops, these are okay, G2 H1 and G5 H2. Okay, so these are the 3 loops. Now, which 2 loops are non-touching? So our step 1 was finding forward path. Step 2 is finding out loops. Step 3 is find the loops which are non-touching. So L1, L3, okay, non-touching. So this also we have identified, non-touching loops. So three steps are over. Forward path we have denoted, then we have denoted the individual loops and then the non-touching loops. Okay. Now the fourth step, the loops which are non-touching to particular forward path. L1, L3 है ना, uh, L1, L2. Okay, so loops which are non-touching to forward path. Now there are multiple forward paths, but out of them there are some forward paths where some of the loops are non-touching. Clearly, you can see this. If this is the forward path G1, G2, G3, then this loop G5, H2 will be non-touching. Similarly, if we have forward path G4, G5, G6, then the loop G2, H1 will be non-touching to this forward path. So there are some forward paths to which some of the loops are non-touching. Okay. So I'm keeping this just for a few seconds. You can check this and then I will go to next page. Okay. So the forward paths are calculated, loops are calculated, non-touching loops are calculated. Now just substitute everything in our formula. So it will be T1 delta 1 plus T2 delta 2 plus T3 delta 3 plus T4 delta 4 plus T5 delta 5 and plus T6 delta 6 and whole divided by delta. Okay, everything we have calculated. T's are calculated, L's are calculated, and we have seen that only two forward paths are there to which there are non-touching loops. So remaining deltas are just one. Okay, so these which are non-one, not one, that I will write here. Remaining are one. So delta one is the forward path, which is this G1, G2, G3, and to this forward path, the loop which is non-touching is this loop G5H2. So here it will be, this will be equal to 1 plus G5H2. Why the formula is 1 minus, but there is already minus sign here, G5H2, so it will be plus. Similarly, what is the next? Delta 3. The forward path is this G4, G5, G6. G4, G5, G6. So this forward path, this loop is non-touching. So its formula will be for delta 1 plus G2, H1. And remaining all delta are 1. So delta 2, delta 3, delta 4, delta 5, delta 6, they are all 1. So just substitute them. So this will be equal to T1 plus T2 plus T3 into 1 plus G2H1 plus T4 plus T5 plus T6. And here we will have 1 plus G1H2, uh, G5H2. Where it is gone? Hmm. Okay, and divided by. Now, what is delta? Delta is 1 minus summation of all loops. So 1 minus L1 plus L2 plus L3 because we have three loops plus summation of all loops which are non-touching to each other. That means L1. Okay, so L1, L2 are the non-touching loops and total loops are L1, L2, L3. So that's our TF. Now the only thing is we need to substitute this L1, L2, L3 and T1 to T6. So these values we need to substitute. So that I am not doing to save the time. You can substitute these values of T1 to T6, L1, L2, L3, and that will be the final transfer function. Okay. So this example is just shown to demonstrate how a complex graph where you will have multiple forward paths and multiple loops, some are non-touching to forward path, how you can solve it. Okay. The point I want to emphasize here is one, and this will be my final point, then we will stop. For the signal flow graph, please understand this. This is a very important point, and you might not have given a thought to this. Okay, this is the signal flow graph. Now, this signal flow graph, these are the two nodes in between the gain is 1. Similarly, between this gain is 1, gain is 1, gain is 1. In this kind of things, what simplification you can do is you can shift these nodes here if the gain is 1. Okay, there is no gain there. So this graph is equivalent to the graph which I will draw now. Minus H2, G4, minus H3, and this is G1, G2, G3. See how simplified it has become. This looks messy, but you can simplify this kind of thing and convert into a simplified signal flow graph. So always whenever signal flow graph is given to you, you first check whether you can simplify it. The formula for simplification is if in between two nodes, if there is gain which is unity, then you can shift this node here. Okay, you can combine these two nodes if the gain between them is 1. and you can have a simplified graph, and then you start solving it. Okay, so that is one. You can simplify the signal flow graph. Second point, and this you should remember, block diagram can be converted into signal flow. Any block diagram you can convert into signal flow. That is possible. Any block diagram you can convert into signal flow. But the reverse is not always possible. All the signal flow graphs you cannot convert into block diagram. And this is one example. This is actually signal flow graph is obtained by converting from block diagram. But after this conversion, we could simplify this, and we have simplified signal flow graph. Now, if you try to convert this into block diagram, it will not be possible. Okay, can you see the reason? Reason is this. If you see, if this is converted from block diagram, you can understand here the path is coming. That means here you have summing point. Here the path is going out. That means here you have takeoff point. Here there is summing point. Here there is takeoff point. But now we have combined this summing and takeoff together here. So in block diagram, summing and takeoff cannot be combined together. Summing is different, takeoff is different. You cannot club together. But once you convert into signal flow, then there is no notion of summing point and takeoff point. They just become nodes. And these nodes you can combine. And you can have simplified graph, which is not possible in block diagram. You cannot combine summing and takeoff. And that is why all the block diagrams can be converted into signal flow, but all the flow may not be, it is not possible to convert into block diagram. Reverse is not possible. That you have to understand. Okay. So with this, I will stop. Again, if you have any doubts, I will answer them. Otherwise, from my side, it is over.
Hello.
Yes,
Sir, am I audible?
yes,
Sir, thank you so much for your um, kind support and the lecture that was given today on the control system topic. I hope that it would be really helpful for our students to take the takeaways from this today's lecture and use the tricks that you have shared with the students. I think it will help them to solve the problems related to the control system. Now, I request any students, if you are having any doubt, like Tejaswini has asked about the signal flow graph, and sir has very explicitly shared the signal flow graph and the procedure how to solve the signal flow graph with the tricks also. So if there is any questions from anyone, students, please reply it. We will be circulating the attendance link in a very short while after the queries are over. And also, we are having the details of our respected expert with us. If you have any difficulty, you can get in touch with me so that I can share the questions with sir at any point. And thank you so much, sir. We would like to be associated with you in future also for this type of lectures.
sure, sure. Thank you. Thank you. I hope
Thank you so much.
this was helpful to all the students. And if there
Sure,
are
sure,
doubts,
sir.
I am
Sure.
ready to help them.
Yes, yes, sir. Okay, thank you so much, sir.
Okay.
Now I'll share the link for students. Please be connected. Okay, so I have shared the attendance link. You all can give the attendance. And for all the students, tomorrow we have scheduled the lecture of microprocessor by Dr. Andy Gaugave from Government College of Engineering. Time will be conveyed to all of you well in advance, so please get in connected on time. So thank you, sir.
Yes, thank you. Should I log out now?
Yeah, 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 sure. So sure, sir, no problem.
Okay.